All right, hey everybody, nice to see everybody. So, today is Tuesday, yes?
Yes.
And then tomorrow's Wednesday, and the day after that is Thursday, see?
We can count.
We can count.
Whoa, you can?
But don't tell anybody, especially with the state, because they'll just want to track you. So Monday or Tuesday, Wednesday, Thursday, today, tomorrow, and Thursday will be our last days of lecture. We will then have a review on Friday. Monday we will then have our quiz, our test on this unit, which is awesome. Then starting next week on Tuesday, Wednesday, and Thursday, we will be reviewing for our final exam. We have the free response portion of the final, and yeah. Right, so it'll be Wednesday, not next week. Yeah. We don't have one? No, it's 2 weeks. But, you know, all right, so let's start finishing up this stuff. Of course, a lot of this information that we're working on kind of is the summation of things we've worked on. We're talking about lines, and that was first semester. Talking about parabolas, that was second semester. Talking about exponential equations, and some things to remember. You know, if I have x squared or ax squared plus bx plus c, is that an exponential equation or is it a quadratic? What's the difference between an exponential equation and a quadratic? X squared. Yeah, 2 raised to the x. So an exponential function, the variable, the unknown, the letter is what the exponent is. So that's the raised power. Okay, so linear, quadratic, exponential functions. Interpret the functions in the context. So you all have that sheet that I handed out. I hope. Sweet. This is a whole bunch of slides. Let's see. What kind of function is it? It's quadratic. Okay. Is anybody sitting there like going, I have to get quadratic out of that? So things that you do know about it, this was some sort of x squared. Actually, it was a negative x squared. Why am I saying that? It's opening down, okay? And yes, there could be something in front of, you could have negative and a number and then x squared and then a whole bunch of other stuff. The domain. And the domain, so the domain and range really are what most students will struggle on. You'll struggle on it in here, in geometry, in Algebra 2, pre-calc, even calculus when you get there. Domain and range are just, when you look at a picture, it's easy to see. Domain and range, when you are looking at an equation, are harder to see because it doesn't tell the whole story. But the domain is basically, if you were to drive along this line, and of course, this graph is going to continue forever down this way and forever down this way. Think of the domain like this. And yes, the domain on most problems that we work on here will indeed go from negative to positive infinity. So if I were to drive along that line and I were able to look above and see the graph, or look below and see the graph, or if I can see the graph right on the line. So as I'm driving here, think about right this. And I'm going to put a dot there, and I'm going to put a dot there. Okay? And I want you to think about this. The domain, as I'm driving, is all below this line, so I'm making it negative. And then here, it's all positive. And then as you get over here, it goes back to negative. And where the dots are is where it lands exactly on the line. So the domain, as I drive, sometimes the graph is below the line, so we'll list that as negative. And sometimes above the line, we'll list that as positive. Sometimes it lies right on the line, so we'll list that as just a solid dot. So the domain is always going to be negative to positive infinity as far as a quadratic goes. But the range is then where it's so hard to fathom what's taking place with the range. And the range, you are going up and down this. Okay? So sometimes the graph could be taking place on the right side of it, and sometimes it could be taking place on the left side of it. Agree? So what you have to think about is, if I have taken this elevator all the way down here, if you were to look out to the right or to the left of the elevator, would you indeed see the graph? And if I were to take that elevator and keep going down and going down and going down, is there ever a point with how this graph is sitting that I won't see my graph on either the right side or the left side? So the domain, or the range itself, is going to come from negative infinity, but as I take the elevator up, so let's just see. I can see right side, left side, 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 right side, right side, right side. Can't see it. 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 Why can't I see it? It's not existing out on those planes, okay? So up to this point, which I think, is that a 5? I can't see it on mine. So does it look like it kisses right here? So the range is going to go from negative infinity all the way up to what? Positive 5. And does it include that 5?
Yes.
Yes. It kissed that line, so it touched it once. Okay, so that's what our range is doing. So the range is like an elevator. And if you had windows on this elevator and you were able to look at either side and see the graph, that's where the range is going to exist. Okay, of course, if the parabola opens upward, we're gonna flip-flop this. Okay, if it opened upward, because it would start at a certain value and continue upward. The maximum or minimum values of the function at x. Well, f at x is the same as what letter? Y. So let's decipher this to be y. Okay? So in the y direction, what do you think the minimum value is? Do I ever get there? So I don't really have a minimum value up here, correct? I mean, to say negative infinity, that's just a place you're going to, but you're never going to get to. My maximum value would be what? In the y direction. What's the highest value I get to in the y direction on this graph? 5. Okay? And then the roots are, where does it cross the x-axis? They don't always have to be whole numbers. They don't always have to be rational numbers. They can be irrational, which means I know about where they cross, but it's some decimal that goes on forever. So on this particular graph, it looks like the roots are where these circles take place. And being you can't really see exactly where it takes place, I would say it would be safe to say that our roots in this case would be irrational. Okay? If they crossed right on a thing, or right in the dead center, and you know it's right in the dead center, but neither of those do. But my roots were across the x-axis. The vertex has an ordered pair. Anyone want to take a shot at that? The vertex has an ordered pair. What's the point of my highest point? Huh? 1, 5, right? Does that make sense? 0 gives us the value of 4, it looks like. The equation of the axis of symmetry. A couple of you struggled with this yesterday. You couldn't remember what the equation of axis of symmetry was. The axis of symmetry is the line, the vertical line that I can fold. Yeah. Perfect. It is the equation x equals 1. It goes along with the x component of the axis each and every time. And then we want to know where the intervals where x of x, where the function at x is increasing. Okay? So I'm riding this roller coaster up. I'm increasing, I'm increasing, I'm increasing, I'm increasing, I'm increasing. I get to this horizontal. Then I'm no longer increasing nor decreasing. and then I'm going to start going down. So from the x direction, where am I increasing on this graph? Where am I coming from in the x direction? I'm way out here. The graph is increasing. It's going up. So what's way out here? Negative infinity. Where am I increasing up to? But in the x. Where's it increasing to? In the x. Where it's increasing. And where? What is that number? So, there you go. So the graph itself is increasing right there. It gets right up to that point. So that whole region is increasing. It's decreasing from 1 to negative infinity, but this is where it was increasing. It's heading up. Okay? Is there any questions about that? I know we've worked with parabolas quite a bit. You know, things that parabolas work with, quadratic formula works with it. Factoring works with it. The negative b over 2a comma plug in works to find the vertex. The axis of symmetry is the x component of the vertex each and every time. Okay? So just a few things. May I move off that screen? Still there? Okay. What kind of graph? Exponential. Okay? So this is some number raised to the x power. Okay? So where do you feel that this is going to? Infinity. So as I go this way, could I still continue to look up and see that graph? It's growing a heck of a lot. It's going to be really far away quickly, but the domain of this graph looks like it's going to come from negative infinity and get to positive infinity. So as I ride on here, either direction, I'm going to be able, with this particular graph, look up and always see my graph. Okay? It doesn't stop. Like if I were to have a really enormous piece of paper, I could say, I'm going to continue drawing straight up. Look at that. I'm going to continue going this way. It's going to keep going. Okay? What line does it appear that it is coming really close to, but it's not going to cross it? Yeah, good. So right here, look at this at number 4. It appears that it's going to go right along this line. It's going to get really close to it. Okay? In calculus, it's called the Squeeze Theorem. And another cheap version of it is called the Fly-Swatter Theorem. You get really close to something, but you don't get it. You ever try smashing flies with the thing? Every now and then you get lucky and everyone gets grossed out because you see it go every direction. But sometimes you honestly realize that this fly has some sort of magical power of knowing that you're going to squish it. What about the range? What about the range? The range has something to do with the horizontal asymptote. So where I'm on the range, we're going up and down this elevator. Going up and down this elevator. So if I'm riding this elevator up, can I look out either side and see the graph yet?
No.
As I come up here, can I see it?
No.
What about when I get right to 4? Can I see it yet? Think about that before you answer. If I get to on the y-axis, the number 4, if I look out and I'm looking right along the axis, and right along the axis of 4, the line y equals 4, can I see the graph yet? Something's getting really close to it, but it hasn't crossed over that line. So my range is going to be a round bracket from 4 all the way to infinity. So as I get a little bit above this line, I'm going to start seeing the graph out that side. And as I continue up, I'm going to still see it out that side. Now I see it on the line. Now I start looking down at this side, and that's fine. So my range is a rounded bracket at 4 because I will never get to 4. I'm at this infinitely close fraction to 4, but I'm not going to get there. So our equation of our horizontal asymptote, so hang on. So here we used x equals 1 because x equals 1 is a vertical line. What is a horizontal line going to be? Y equals 0. You're close. You were so close. And the reason you're close on the Mac, this one we shifted up though. So what do you think I'm getting close to? Y equals 1 is right here. Y equals 0 is right here. Y equals negative 1 is down here. Yeah, I want to know what the equation of my horizontal asymptote is. That's that green dotted line. What number? Yeah, y equals 4. So that's the line that we will never cross over. We're going to get really close to it. Bless you. But we're not going to get there. Bless you. So, critical thinking moment. If I am never going to cross over the horizontal line y equals 4, will I ever cross the x-axis? If I will never cross over the line y equals 4, it's this horizontal line right here, will I ever cross the y-axis? No. I won't. So, do I have any roots? No. And I would label this to be correct, no real roots. Okay? And remember, a real root will cross the x-axis. It could cross the x-axis at an irrational or a rational spot, but I don't want to say that there's no roots at all, because there could be some sort of imaginary or complex number root, meaning it's going to have a square root of a negative number. Growth or decay? Decay. Why do you think? It's coming from a really big number and coming down. So this is decay. There's a kind of math. It's called discrete math. It's actually a relatively interesting math because you do work with real life scenarios, and I used to teach it for quite a few years. And you use growth and decay models, but then you use something called the matrices in order to determine if a species would survive or not. So let's say you decide to you work with, I don't know, dolphins. I'll go with that. I like that. So let's say you're going to work with dolphins. So what you're going to do is you realize you have the male and female species, and the male and female produce offsprings. They have babies. If you were to say, look at these particular dolphins, and you can sit there and track a certain amount of the species, and you realize that there's a certain age that they will, average age they will die off at. There's an average age when they can start producing offspring. And there's an average age where there's a survival rate of the birth. So just because the dolphins produce an offspring doesn't mean that offspring will survive. There's a certain probability that offspring will survive. But what this math allows you to realize is there is no way or a way that this species could continue to survive. This is something they did with bison. A lot of people know bison is buffalo. Okay, but it's actually called a bison, right? So these herds of bison, we almost eradicated the entire species. We killed off the species to a certain limit that it was almost impossible for the species to be able to reproduce and its generation to survive. Okay? Paris, France. The French. Let's talk about the French. We all love the French. Do you know that right now that though you have people who are immigrating into the country of France, that the bloodline of the French it is impossible for the bloodline of the French to continue? Now they will continue to have babies, but they cannot have enough babies to survive the bloodline of the French. So it might be 3,000 or 4,000 years before the bloodline of the French goes out, but by using something called the Leslie matrix, which again takes into account the birth rate, the survivability of the birth rate, the death rate, the amount of offspring, and it's just this real interesting type of math, and it all again goes along with exponential growth and exponential decay. I mean, I think that's an interesting thing, and people, when I used to teach this class, they're like, yeah, but if you look at the country of France, the population is increasing. Yes, because people are immigrating in. There are certain Native American tribes in the United States that will indeed die off because, well, one, we've reduced it. Some of the people from their tribe have left their tribe and moved to join other tribes. That's just kind of the way it is, but it all goes along with logistical thoughts of how math works. Okay? Last slide. Ready? Identify, for the graph, identify. What kind is it? Linear. Yeah, it's a straight line. It's linear. And if you remember on that quiz yesterday, we asked, is it linear, quadratic, or exponential? And I'd say almost everybody knocked it out of the park. A couple of you are kind of like, it looks like a parabola, but I'm going to call it a straight line just because I haven't used L in a while. That's not always the right way to go. The slope. The slope is also known as the rate of change, correct? And the slope is always constant on a line. It's not constant on an exponential function. It's not constant on a quadratic. Okay, but the slope of this line, it's the rise over the run. So you find a point. Oh, that looks like negative 3, 0. And you find another point. It looks like it goes right up there. So I went up 1, 2, over 1. So I have a slope of 2 over 1. No matter where I am on this line, 1, 2 over 1. Up 2 over 1. Up 2 over 1. But if I went back to this graph here, look at my slope here. I'm going to go down 1, 2, 3, 4 over 1. But if I go down 4 from here, 1, 2, 3, 4 over 1, it's not going to work. So our slope's not constant up here. Our slope on this one is not constant as well. So if I went up 1, 2, 3, 4 over 1, if I went over 1, 2, 3, 4 over 1, no, it's still not constant. So the linear is constant, the quadratic is changing, slope, the exponential is changing, so the rate of change is changing. The roots. The roots. Does this particular line cross the x-axis? Yes. Where does it look like it crosses the x-axis?
1.5.
About 1.5. I like it. So 1.5, comma 0. Why am I putting the 0 there? Yeah, it's not. It's on the x-axis, so it's not moving up or down in the y direction. And the intervals where the function of x, where the function of x is increasing. Increasing, remember, is heading upward. Yeah, this one has an interval. The whole thing will go from negative infinity to positive infinity, where it's increasing, 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 increasing. Good to go? Feel all right about this? I'd like to give you the opportunity to start on your assignment. Is that all right? If you happen to get your assignment done in the next 21 minutes, it means you're walking out of here without any homework from me. And I know most of you cry yourself to sleep, but you know, hey, feel it. No.
Oh, damn.
I've been shocked.
Oh.
All right, your assignment is page 145 through 147. If you need a picture of it, I have it up here. I'll put it in this basket. There's the front and the back. Cool? Good to go? You guys want to work on the assignment? Please do. Enjoy.